Hello, everybody. So we're still talking about the pump or the pipe network problem. In the last videos, or yeah, the last video we were done with this part of the flow sheet, and we did some manual calculations using Microsoft Excel to validate the results and make sure that we understand how the calculations are going. In this video, we are gonna go for the rest of the flow sheet. Just for the sake of time, I did all the connections for the two splitters and the four pipelines or the four pipes because it's just a routine process of connecting or adding some units and connecting them. So I didn't want to waste a lot of time in doing that in the video, so I did that beforehand. And what we're gonna do is to define these four pipes and see how we can define them and see the results and how the results are going. Let's see. So here is again, this is the flow sheet, and the part that is not defined is starting from 6 and 7, from the two splitters and the four pipes. And let's see what we have for the splitters. So the splitters, what we need to know about the splitter is the split fraction. And this is what we have here. So let's go to Aspen Plus. Where is it? Oh, here it is. So I'm gonna put them side by side just to see both of them. So what we have for splitter S2 is that the stream number we have here 8 and 9. So I know that's stream 8. The split fraction of stream 8 is 0.7758, and I'm done with S1, and now S3 I know that 0.6428 goes to stream 11. Of course, it doesn't matter mass or moles or volume, it's going to be the same ratio for all of them. So we're now done with the splitters, and now we need to go for the pipes. Just from a quick look at the definition of the pipes here, we will realize that they are pipes, not pipelines. And we talked about this difference before. In the pipes, they are just one segment, and that's why I define them as pipes, not pipelines. Of course, you can define them as pipelines, but it's going to be one segment pipeline, which is a pipe. So it's a good chance to see how we can define both. And here we need to define only the length, the inside diameter, and the elevation change. So 44, the length is 10.73 meters, the inner diameter is 1.5 inch, and again, make sure that you change the units because it's a very, very common mistake. If you keep it as meter, it's gonna give totally different results than what you should expect. One other thing that I forgot to do is to make sure that it is liquid only to prevent the warning that comes at the end of the run. For pipe T5, the length is 0.75, oh no, it's 10.73, I'm sorry. Meters, the diameter is 0.75, again inches, and this is liquid only. Now T6, the length is 14.95, the diameter is 2 inches, and liquid only. The last one is T7, the length is 3.9 meters, inner diameter is 1 inch, and for all of them we have 0 elevation change, so I didn't point any value here, and we should be good to go, and I will run the file and see what we get. Now the results are available, so it's done with the calculations, we don't have any issues. And let's take a look at the results. So for T4, for example, we have again, the pressure drop is totally from the frictional pressure drop. We don't have any other sources of pressure drop, as we mentioned before, because this is there's no elevation, and there are only two types of pressure losses that we should expect. This is gonna be the same. We wouldn't expect a lot of results here. Just the stream results. We can find the pressures, which is already we can get from here. We can find the temperature. The velocity is almost 4 meters per second, and yeah, I can see the flow related, the Reynolds number, the friction factor. These are numbers that we can check from the Excel file. So I've already put some results here, or the data here in the Excel file. I added the flow rates of all the streams here, or all the pipes. And here is T4. I put the diameter, I put the length, but I didn't do the goal seek to or solve for the friction losses. So I'm gonna go here for goal seek, put the equation exactly like we did in the previous video as 0, and I would change the friction factor to satisfy the equation. And it's here 0.022, and here it's 0.02198, which is pretty close actually to the value that we and here you see the exact value 0.21986. It's 0.02198.5, so it's almost the same value. And for the Reynolds number, we have here 168,780. 5, it's 168,900, so it's pretty much the same value. And for the losses, let's take a look at the losses. They are automatically calculated. I have them as Pascal, so let's go here for the results. Go for the summary, and you can put it as Pascal. It is 4,800 and 144. It's 4,800.089, which is very close actually to the value. I don't have any elevation pressure drop. For instance, if the pressure at the other side of the stream, or of the pipeline, which is stream 12, I can find the pressure equals in Pascal. It's 54, or let's put it as, yeah, it's 544. It's here 544, 528. It's 543,081. Again, pretty close to each other. One last thing here is if I make some elevation changes. For instance, I put here the right hand side as 4 meters. I'm just trying any number, and here I can, for the setup, I can make the pipe rise is 4 meters. Again, it's good to see what we have. If it says here, let's you type the change in the pipe elevation from pipe entrance to exit. Flow is uphill is positive, which is important. If it's going to a higher place or a higher elevation, you have to put it as a positive value. So this is 4 meters. I'm gonna run the file, and let's take a look at the results. Here you'd see there are some elevation pressure drop, which is here 39,227. It's 39,122. Again, pretty close to each other. This showed up because we have some elevation change. If we flip it, just to make it go the other way, if I'm 4 meters higher in the entrance than the exit, here in the setup, I'm gonna make it as -4. And if you run the file and go to results, you'd see that there are no elevation pressure, or it's a negative pressure drop, and the total pressure drop is going to be lower than before. It's 8,917, which is before it was 48,000, and this is because there is higher elevation, and this makes the pressure on the left hand side, or the energy on the entrance, higher than the energy in the entrance in the previous case, and this reduces the pressure drop, of course. Anyway, so this is all for the pipe network file. We saw how we can, or problem, we saw how we can define the pumps. We saw how we can define pipes and pipelines. We will do one more video just to take a look at the valves and maybe the compressors, just to make sure that we cover all the parts related to the pressure changes. So this is going to be the topic of the next video, inshallah. So I'll see you then. Goodbye.